Okay, so the first of a couple of lectures on antioxidants, second one of which will be substantially longer than this one. A little bit of revision about biochemistry to start with. This is sort of stuff you've done in biochemistry, but it's been a while ago, so you might have forgotten some of it. We'll talk about the nature of biochemical reactions and how we document them, talk about oxidation reactions, the importance of NAD, and a few other definitions of oxidation. Okay, so biochemical reactions. Some basic definitions to start with. These processes can be very simple, or they can be very complex indeed. Even the more complex steps, it has to be said, are often composed of a large number of small changes. Chemical reaction involves the breaking and formation of chemical bonds. There are a lot of biochemical reactions, a real lot. This is the famous Sigma-Aldrich metabolic pathways map, which is impressively complicated, although mostly only deals with energy metabolism, so it doesn't include many other aspects of human biochemistry. The point about this is, though complex, every reaction here works on basic principles outlined in the previous slide. You can obtain the map from the link in the notes in the usual place, or clicking through just for fun. It's quite an impressive piece of work. So some revision. Chemical reactions. In this generic reaction, we have two reactants A and B, which undergo a chemical reaction to produce a single product C. The number of reactants and products may vary depending on the particular reaction, of course. The reaction takes place under certain conditions. In this case, a temperature of 100 degrees centigrade is needed, and it's a particular direction, from reactants to products. As we'll see, more complicated directions are common in biochemistry. So in biochemistry, we call reactants substrates. Most biochemical reactions are at least potentially reversible depending on the conditions, which is why, instead of using a simple arrow pointing in one direction, we use two half arrows pointing in opposite direction. Most biochemical reactions you see will use this convention. The direction, it has to be said, generally speaking, depends on the conditions. Here the conditions indicate it needs the molecule adenosine triphosphate, ATP, and one of a class of enzymes called kinases to go from the substrates to the products. And you require a different set of enzymes to go in the other direction, probably another kinase enzyme. So biochemistry is a little bit different to the general chemistry. Sometimes we indicate the direction of the reaction by the relative length of the lines. In this case, we've shown the reaction going very much from the substrates to the products. It could go in the other way, indicated by the forward line being shorter than the reverse line. To do this, as I mentioned, a different kinase enzyme, an ADP rather than ATP, would be needed. Different conditions, different enzymes to go in the opposite direction. Most biochemical reactions are part of complex reaction pathways. Again, see the Sigma-Aldrich poster. They are multi-step, with most reactions being reversible. This is the outline pathway for glycolysis, a key pathway in energy metabolism. There's no need to worry about the details. You'll cover this in second year. The take-home message here is that biochemical reactions are often very complex, and this is especially true with claims about the role and the effectiveness of substances which are claimed to be antioxidants. A bit of a leap there. As we will see later, the chemistry of biological oxidation is very complex indeed. And for example, many antioxidants can also promote oxidation, depending on the biochemical circumstances. And what we'll put there in red is a good basis to think about all of these things. When people make claims, there's often not a lot of science behind them, unfortunately. Oxidation reduction reactions are key to life. And I'm sure, as you remember from biochemistry, when an oxidation reaction takes place, it is always linked to a reduction reaction, and vice versa, obviously. We call this a redox process for reduction and oxidation. So this is the simplest definition, and hopefully it's straightforward. Here's a simple reaction from general chemistry. The burning of ethane, C2H6, in oxygen to produce carbon dioxide and water. What we need to think about, which element is being oxidized and which is being reduced. So we tend to worry about things like carbon and oxygen. So if we put in the little indications of what's happening, think about the carbon atoms in ethane. At the start of the reaction, they're all bonded to hydrogen atoms. You might want to draw out ethane, the molecule, to confirm this. But in the end, they are bonded to oxygen. I've got oxidation in the notes. They are bonded to oxygen. Hence, carbon is oxidized here. Conversely, oxygen is all in its own at the start, but reacts with hydrogen to produce water. Hence, oxygen is reduced in the reaction because it has gone from having no hydrogen to having some hydrogen. And overall, it is a redox reaction. And there's a definition there. Oxidation is gain of oxygen, reduction is loss of oxygen. Or conversely, oxidation is loss of hydrogen and reduction is gain of hydrogen. There are a number of different definitions here. So we'll look at why this matters. This is glucose, a very important biological molecule with the formula C6H12O6. The atoms in the glucose molecule are arranged as shown. Note that each carbon atom has has OH groups attached to it. There and there, for example. In the terms of our discussion of oxidation and reduction, note also the hydrogen atoms attached to the carbons. That, etc., etc. As you probably know, this straight chain molecule is glucose as a solid. In solution, it forms a ring. Biological molecules reactions happen in solution, of course, but it is perhaps easier to refer to the straight chain for our discussion here. And the structure of CO2 is also included here for reference. So there's the ring form of glucose. In this case, it's probably easier to use the straight chain form. Cellular respiration. This is the most important reaction in animal biology. Obviously, photosynthesis is vitally important in general biology. Note that respiration is a process that takes place at cellular level. Breathing, the process of taking air in and out of our lungs, is not synonymous with respiration, though is often necessary for the process. When we eat sugars like glucose and oxidize their carbon atoms to produce carbon dioxide and water, we also regenerate the molecule ATP. Again, the details here are out of scope here and will be covered in year 2. For now, make sure you understand that oxidation and reduction processes are taking place. Pause the video, the presentation, have a think about what's being oxidized and what's being reduced here, again in terms of the carbon atoms in glucose and oxygen. Okay, so I'll assume you'll have paused the video there and we'll move on. So again, this is only slightly more complicated than the earlier reaction. Simply put, each carbon in glucose is bonded to one oxygen. Look at the formula to confirm this. After the reaction, each carbon is now bonded to two oxygens, beg your pardon. Hence, oxygen has been oxidized. As with the earlier reaction, oxygen from molecular oxygen over here is now bonded to two hydrogen and water. So this oxygen has been reduced. Again, the overall process is a redox reaction. Since we mentioned photosynthesis, here's the equation. We'll use this to explain a second definition of oxidation and reduction. I mentioned briefly earlier, this in terms of whether hydrogen has been gained or lost. And the definition is at the top of the page. As we saw earlier, the carbon atoms in CO2 are attached to two oxygens, and at the end these carbon atoms have been incorporated into glucose. So in terms of the second definition, carbon has been reduced because there's a lost oxygen. Now look at the oxygen in water. It starts attached to two hydrogen and ends up attached to just as molecular oxygen. So in terms of the second definition, oxygen has been oxidized because there's lost hydrogen. I think I did get that right. I'm not sure I did. Let's go through this again. So carbon starts off being attached to two oxygens and it ends up losing the oxygen attached to hydrogen, so it's been reduced. Whereas oxygen in water is being oxidized because it's lost the hydrogens and has gone to just being molecular oxygen. Right, okay. So how does this happen? As you know, most biological reactions need enzymes to catalyze them. Many reactions, especially redox reactions, need a molecule called a cofactor, and there's a definition there. This is NAD, otherwise known as nicotine adenine dinucleotide. Everyone calls it NAD. It's a cofactor and is involved in numerous biological oxidation reactions. Don't worry about the complexities of the molecule, although you might notice in passing it contains two copies of the nucleic acid base adenine joined by sugars and phosphate groups. The molecule exists in two forms, the oxidized form, which we call NAD+, and the reduced form, NADH. Yeah, so it's reduced because it's gained a hydrogen, basically. Yeah, this one here. It all looks very complicated, but in a chase of molecule is loss or gain of a hydrogen atom, and the hydrogen atom which is lost or gained is, I think it's going to click here, yes, this one. So over here we have NAD+, NAD+, and over here we have NADH, which has gained an extra hydrogen atom. For simplicity's sake, the reaction is almost always written in this form. We've ignored most of the molecule and just concentrated on what changes. Conversely, if NADH loses hydrogen, it is oxidized back to NAD+. Okay, here's another definition of oxidation reduction, in this case in terms of the loss or gain of electrons, and it's one that's used a lot by general chemists. And here's one of the most important reactions in biology, the formation of water, included here for completeness. You'll probably review this again in more detail in Year 2 Human Metabolism. If you're interested in this, you want some more background, the Chem Guide's not a bad, a really good actually link on this. There's lots of good stuff in Chem Guide, and it's fairly straightforward. Right, that's all for this introductory phase. I'll be back in a moment.